Hello, my name is Terry Soul, and this is Programming Chaos, a channel devoted to projects that you can use to hone your programming skills. Today's project is reaction-diffusion models, which model the interaction of two or more chemicals and are used to make interesting, as you can see, colorful patterns. They're often used, for example, in, say, games or artwork to generate the kinds of patterns that are seen on animals. So this, as you can see, looks a little bit like perhaps zebra stripes. And so gives you a good method by changing the parameters within the model to generate all sorts of different organic looking patterns. Okay, the general idea is we're modeling how two or more chemicals interact. Our model is divided into cells, so you can see in the image individual cells, and each cell contains the concentration of two or more chemicals. So in this case, we have a red chemical and a green chemical, and the amount of red and the amount of green defines the concentration of each chemical within each cell. And then we model both a reaction in which one chemical changes into the other one, and a diffusion process in which the chemicals diffuse from their current cell. And to be able to program this, we need some more details about exactly how that reaction and diffusion takes place. We'll have to do a little math to understand how that works. If you want, you can skip over it, but it's helpful to understand exactly how the code works. There are many different reaction diffusion models. I'm going to be using the Gray-Scott model, which is one of the simpler ones, and it models the interaction of two chemicals. I'll just call them chemical A and chemical B. What we need to do is understand how the concentration of each of those chemicals changes in each cell. And so these are the mathematical equations. Sorry, you got to bear with me on these, for how those concentrations are updated. And so the idea is for chemical A, the concentration at T plus 1 at the next time step within a cell is defined by this equation. Looks a little messy, not quite as bad as it seems. So the idea is the concentration for A at the next time step is equal to the concentration at the previous time step. And then we change it according to these other terms. So the second term here, which looks a little odd, is the diffusion term. Basically, it says some of the chemical in a given cell diffuses into the neighboring cells. There's a constant out front. This is a diffusion constant, which is sort of how much of the chemical diffuses. And then this weird symbol here with the 2 just says we're doing diffusion in 2 dimensions. And I'll talk in a minute about exactly how that diffusion is applied. And then, so this is the diffusion part of the reaction diffusion. And then we have the reaction part. And so this term is chemical A becoming chemical B. And you'll notice for chemical B, this is how much chemical B we have at the next time step. It increases by the same amount. So we lose some chemical A and it becomes chemical B. If we just did that, we would quickly run out of chemical A because it would all become B. And so there's another term here. This is sometimes called the feed term, and F is the feed parameter. That's how quickly we're feeding chemical A back into the cell. F is just a parameter, and then this 1 minus A basically means if the concentration of A reaches 100% concentration, then this term becomes 0 when we stop feeding any more chemical in. So all we have to do is apply this relation to each cell in the grid, and that's how the amount of chemical A changes over time. Chemical B, very similar. We start with the concentration at the previous time step. We diffuse it into the neighboring cells according to some parameter in front. And so the way this Gray-Scott model works, this value dA will be 1. So basically we're going to allow all of chemical A to diffuse, and this parameter will be 0.5. And then chemical A becomes chemical B, so this is a plus term. We have the amount of B increasing. And then if we just did that, the amount of B would increase indefinitely. And so we have a negative term where some of the chemical B is removed from the system. And we use the F parameter again, so it's tied to the feed rate, and then an additional parameter K, sometimes known as the kill rate. That's how quickly chemical B is removed from the system. The rate of removal is tied to the concentration. So if the concentration gets to be 0, we can't remove anymore. And so the minimum concentration, therefore, is 0. Okay? Another way to think about this is you can sort of think of A, instead of being a chemical, maybe it's like a prey species that increases over time, but also is being eaten, and that allows the predator species B to increase over time. So it's a model, and you can think about models in sort of different terms if you want. We also have to worry about how diffusion works, and that's pretty straightforward. Basically, for a given cell, we're diffusing into the neighboring cell. So we're just saying some of the concentration leaves the current cell and goes into the neighboring cells, or, and this is actually how we'll program it, we can think of it the other way. Some of the chemicals from the neighboring cells come into the current cell. And the way that works is for the corner cells, 5% does. So whatever the concentration of A is in this cell, 5% of it is added to the center cell. Whatever the concentration is in this cell, 20% is added to the center cell. And that's symmetric all around. And so when we want to calculate the new concentration of chemical A in the center, we look at what the neighboring cells are and add an appropriate percentage. And then this -1 in the center cell says, well, we're going to remove all of the chemical that was there and only let chemicals diffuse in. And that seems a little confusing, but sort of the idea is all of the chemical here has diffused out, and so I'm going to subtract all of it. And in return, chemicals are going to flow in from the neighboring cells. Is there anything special about these values? Well, they kind of make sense. They add up to 0. So all the ones around the edge add up to 1, and then we have a -1. And what that means is the total amount of chemical A is not increasing and it's not decreasing. It's staying constant. It's just diffusing around the grid, which is what we'd expect. And it kind of makes sense that along the diagonals, there's sort of less contact area, so you get less diffusion, and along the edges, you get more diffusion. But there's nothing special about these numbers. If you wanted to use 0.06 here instead of 0.05 and make this, say, 0.19, so it all adds up to 1, that would be certainly plausible to do. These numbers, as part of the Gray-Scott model, are known to give the interesting patterns we saw at the beginning. But you can certainly play around with the diffusion to try different variations to see how it affects the outcome. Additionally, it's worth noting that this exact same idea is applied to things like image processing. So if you want to blur an image, what you're really doing is applying this exact same model, but instead of thinking of it in terms of the concentration of chemical A, you're talking in terms of the pixel values, the color values. And so you can blur an image by sort of diffusing the colors, or you can sharpen an image. And if you wanted to sharpen an image, most of these outer numbers would be a negative number, and the center number would be a positive number. So it would basically sharpen the image by increasing the values that are already fairly high. In image processing, it's called a kernel or a mask. If you're thinking about things like neural networks, this same sort of pattern is a convolutional matrix. So this general idea of I have a grid of values and each value is going to change depending on its neighbors actually appears in computer science all over the place. So that is the math that we're dealing with. And again, the general idea is simply in each cell, we apply this equation to update the amount of chemical A and this equation to update the amount of chemical B. In terms of the code, I'm going to do this using 4 matrices. One for chemical A and one for chemical B, which totally makes sense. But then, as is usual in updating a matrix like this, when we calculate the new value, we can't store it in the matrix, because if we do, it will mess up all of our other calculations. So if we change the value in the 0, 0 cell and then go on to figure out the value in the 0, 1 cell, the value in the 0, 1 cell is going to be wrong because the value in the 0, 0 cell was changed. So in addition to the matrix for chemical A and B, we need another matrix to sort of store the new values temporarily. And if that doesn't entirely make sense, hopefully when we do the code, it'll become a lot clearer. So that's sort of where we need to start, is setting up those matrices, defining the constants that we're going to use, and then we can start applying these equations. The first thing we need to do is define our variables. There we go. So we have our two-dimensional arrays for storing chemical A and chemical B, and then 2 more arrays for storing them temporarily. These are the next values. So when we calculate the chemical at t+1, we'll store them temporarily in these next arrays. D1 and D2 are those constants that we apply to the diffusion. And then we have the feed rate and the kill rate. And these numbers are fairly standard ones that give us nice, interesting patterns. At the very end of the video, I'll show some other numbers that you can use to plug in there. You can experiment with picking your own, or certainly look up different ones online. And now there's one more set of variables that we're going to need. We're going to need to make each cell a little bigger. And so we need a scale for how big the cells should be. And then based on that, how big our array is going to be, how many columns and how many rows we're dealing with. So there we go. I'll start with a scale of 20, which is going to give me reasonably large cells. And mostly I'm doing that because I'm impatient and I want the model to run fairly quickly. Once it's all working, we can move the scale down and get a finer resolution in our image. So now I can start setting up the code for that. So rows is just the total height of the window divided by the scale I'm using. So now we can define those arrays. So there's the arrays, and now we need to initialize the values, and for that I'll have to loop over all of the values in them, so a couple of nested for loops to take care of that. So here we go. I'm looping over each row, and then for each row we're going across all of the columns. Okay. And now in terms of filling in the matrix or filling in our grid with chemicals, for the most part, we want to fill each cell with 100% chemical A and no chemical B. So there we go. And this won't work. I'm going to need to add some chemical B in at least some of the cells, but this is sort of how I want to initialize things. And notice that when dealing with two-dimensional arrays, they're always listed as row column, and it's very easy to remember. I need R for row and C for column. If my indices were I and J, it might be a little trickier to remember which should be I and which should be J. For our next arrays, we're going to fill those in by doing our calculations, so I can just set those to all be 0. And then I need some of the cells, instead of being all A and no B, to be all B and no A. A common way to do that is just to pick a region in the center and put all of the B there. That gives you nice symmetric patterns if you want. I prefer a more random pattern, so I'm going to do it just randomly picking some of the cells to contain B. So I'll do it with a 5% chance, and it took a little bit of trial and error to come up with that percentage. In general, these reaction diffusion models are pretty sensitive, and small changes can have a big impact. Setting up these models can be tricky because if you make a little mistake, or if you say, I'm going to try some arbitrary parameters, they may not give you anything interesting. So it's good to start with working values, and once everything is working, then you can play around with the parameters. So there we go. That will fill everything with mostly all chemical A and no chemical B, but in 5% of the cells, lots of chemical B and no chemical A. Now that our setup is done, we can start with the drawing part. And that's pretty straightforward. We just want to go through and in each cell, fill it in based on the amount of A and B. And I'll just use RGB. So I'll use red as the amount of A, and green is the amount of B. I need to go through all of the cells, so I will borrow my for loops again, a little cutting and pasting here to save time. There we go. So because the concentrations are between 0 and 1, but our colors range between 0 and 255, I'm taking the concentration and multiplying by 255. And now we just draw in our rectangle. One note here, and this is an easy thing to get wrong, is when we're drawing the rectangle, the column comes first. And so in arrays, it's always stored as row column. So the first number is which row you're in, the second number is which column you're in. But when we're drawing to the screen, the first number is the X value, which corresponds to the column. And so just for drawing, we reverse the order. And now if everything is right, we can run this and we will see a very static pattern. So you can see we have cells, most of them are filled with red, which is our chemical A, and some of them are filled with chemical B. And now we have to put in the process of the actual reaction and diffusion. To apply the reaction diffusion equations, I'm going to create a separate function. I'll just call it update, which will update all of those values for us. And so this is going to go in and set the new values in our A next and B next arrays. And then once all of the values are filled in those arrays, we'll copy them back into the A and B arrays. And so I'm going to need to do that for every cell. So once again, I will simply copy over my for loops. And so the first step is A next is based on the value that was in the cell already. So we simply take the value that was in the cell and copy it into A next. And then the next thing we have to do is handle the diffusion. So this is the basic idea. We take the amount of chemical A, not in the current cell, but in the cell, in this case, to the upper left. We're using our diffusion constant, D1, and then that 5%. So we're saying whatever the concentration was in the cell in the upper left, multiply it by our diffusion constant and take 5% of that and put it in our current cell. And when we put it in, that should not be an equals, that should be a plus equals. So we're adding it to our current cell. And this will almost work fine. This does the right calculation and it adds it to our cell. So this handles the diffusion. The problem, which you may have already guessed, is if the cell I'm interested in is, say, the upper left-hand cell of the whole matrix, that is to say cell 0, 0, when I do this subtraction, it's going to give me cell -1, which is not part of the array, and I'll get an array out of bounds error. So I have to correct for the case where I'm at the edge of the array already. And I'm going to do that by creating a separate wrap function, which wraps around to the other side. So this is going to basically be a toroid model where the edges wrap around. And so I'm going to replace this r-1 with a wrap function that is also given the total number, in this case, of rows, because I'm dealing with the rows here. And creating a separate function is nice because then I can just call that function over and over again, which I'll need to do. So here is my wrap function. It takes 2 arguments, as we can see up here. The first argument is the value I'm interested in, and the second argument is the limit. And that is different when we're talking about rows than when we're talking about columns. And so that's why I have to pass it in as an argument. And then it turns out the function is pretty simple. So it turns out this bit of math here perfectly wraps for either numbers that are too small or too large. And now that I've defined the wrap function, I can use it for both my rows and my columns. And there we go. That should work fine. So I'm looking at the upper left-hand row, but if, for example, I'm at the very top row, row 0, when I diffuse, I'll diffuse from the row on the bottom. And similarly, if I'm in the column all the way on the left, it'll wrap around and diffuse from the column on the right. So that handles the upper left corner. Now I've got the other 3 corners that I have to worry about, so I'll just do a little cutting and pasting. There we go. So that is the four corners all at 5%. And then I have to do the same thing, but instead of for the corners, I do it for the sides. And again, I'll cut and paste and change those numbers a bit. So there we go. That takes care of part of the side. So this is row -1. The column is unchanged, so that's going to be the cell right above. This is row +1. The column is unchanged, so that's going to be the cell right below. And then these two handles the cells to the left and to the right. And the other thing I need to be careful of here is the diffusion from those cells is 20%, not 5%. So that handles most of the diffusion. The last one that we need to include is the -1 from the middle cell. So remember, the center cell had a -1. Basically, we're removing all of the chemical A from it, but it's not necessarily all of it because it depends on what D1 is. So there, these equations give us the diffusion, and really here we're handling sort of diffusion into the current cell because we're adding the amount in the current cell. So the next pieces we have to do are the other terms, the reaction terms. And so the first one was the AB squared, and that's removed from the concentration. There we go. So that is our AB squared, and that is being removed from the concentration. And then we have to put in our feed. So that's our feed term, where F is our feed parameter, and then it was 1 minus the concentration. So if the concentration gets to 1, we stop feeding anything else in. So that handles the updating for chemical A. Now we need to do the same thing for chemical B. And in the interest of not typing so much, I'm just going to cut and paste all of this and then modify it. So here I'm dealing now with chemical B. That's almost all of the changes we need to make. One thing to be careful of is this is chemical B, so I'm using my second diffusion rate. So I have to make all of these D2. Then the next change is for chemical A, we were subtracting this amount. It's becoming chemical B, so we make this a plus. And then finally, we don't have a feed rate. Instead, we have that kill rate. So I'm going to subtract the feed plus the kill parameter times the amount of B. There we go. So that now represents those equations we saw earlier. The diffusion, which is quite a bit of the work, and then the reaction where one chemical becomes the other, A becomes B, and then in this case, B sort of being killed off or removed from the system, and back up here, if you recall, A being added to the system. So this updates all of the values of the chemicals, but it does it into this new sort of temporary next array. For the program to work, we now have to copy those back into our original array. There we go. So that just copies them back over from where we sort of temporarily stored the new values into the actual array. And if I haven't put in any typos, this should run. There we go. So you can see we started with little pockets of green, and then they diffuse, and we get this interaction pattern going. And because the scale is fairly large, we have pretty large cells here. So let's modify that just a little bit. We can come up and change the scale. I'll make it a bit smaller. And you might want to get rid of the stroke as well. So it's useful to see the borders of the cell when you're originally writing the code, just to sort of understand how it works. The patterns you get are maybe a little more interesting without the stroke. So there we go. There's our sort of organic looking forms. And again, we can make the scale even smaller. The other thing that is very often done with these reaction diffusion systems is we change the parameters very slightly across the extent of the image. For example, I'll do it with the kill parameter and I'll set a particular value in the middle, and then as we move to each side, that value will change slightly, so the pattern will change symmetrically in either direction. The other thing that can be done, I started, of course, with random points where we put in chemical B, which means that I get sort of a random pattern here. You could instead start with symmetric distributions of chemical B, and then you'd end up with a symmetric pattern. And you can pick other colors if you don't like this slightly garish red and green, lots of variations. The one I definitely want to show how to code is this one of changing the kill parameter in this case, although you can also do it with the feed parameter. So let's see how that works in code. So the idea is, instead of using K for my kill, I'm going to use a temporary variable. I'm going to define it based on which column we're in. So I'll start with our initial value, and then I'll just add a very little bit to that. And the little bit that I'll add will be based on how far I am from the center column. So columns divided by 2 is the center column. I subtract that from the current column and take the absolute value. So basically, as I move away from the center, this term is going to get bigger and bigger, but I want it to be very small. Remember, our K value is very small, and I want to make a very small adjustment to that. So when I say very small, we'll see if this works. And that is not going to work because I'm not using this parameter. I have to come down here and actually use it. There we go. So I'm not using K, I'm using this temporary K, which varies across the screen. So in fact, if anything, I made it too large. You can see we get the pattern in the middle that we saw before, and then as I move to the side, the kill value gets a little bit larger, which means there's less green. And so we do get a few spots, but not quite as far out as I'd like. So let's make this still smaller. I'll cut it in half and we'll try again. There we go, that's looking a little better. So we sort of have the lines down the middle, and then they fade into polka dots, right? And then towards the very edges, we don't get any green at all. And so if you think about applying this to, say, a creature in a game, what you can do is wrap it around the creature and you get not a constant pattern everywhere, but sort of this varying pattern. And if you think about something like a zebra, right, it has very distinct stripes along its sides, but as it moves towards the belly, they fade away. You see the same thing in lots of fish where you get differential patterns on the back versus on the belly. And we can have that effect just by changing our parameter as we go across the screen. I did it in terms of columns. You can do it based on which row you're in. You can change both the feed and the kill rate to get lots of variation in patterns. So that's our basic reaction diffusion model. And as you can see, there are lots of ways we can modify it from here, but I will leave that to you to play with. Thank you.